So good evening, student. Hope you are doing good. So here we are with our lecture number 4 on simple harmonic motion. So what topic today we are going to deal? We will firstly revise the previous lecture. What we have did. We have seen the time equations and displacement equation and their graph also. And we have also talked about the energies in SHM for kinetic energy and potential energy. We have seen the expressions also. What are the expressions for kinetic energy and potential energy and total energy? And we have found out that the total energy of the system remain conserved. Okay, I'll do that. Just a second. Just a second. Now it is good. Make sure the screen is visible to you and audible to you. So where have you been? Because it's, I think, 3 lecture has been passed for simple harmonic motion and you haven't joined for the single one. Yeah, you're welcome for this, but where have you been? Are you all right? Okay. You're doing your practicals, huh? EWT. I think unit test will be there, no? Okay. So, have you joined through the projector or individually you are joining this meeting? Okay. So, no problem. We are with the lecture number 4 here. Now, if I talk about on oscillation, we have did this one. We are going to see. This is the revision today that we are going to do. Okay. So in the previous lecture, we have seen the time equation of SHM and displacement equation of SHM. Now, what is the difference? Here you will see that every physical quantity, every, let's say the displacement, velocity and acceleration, these all are variable with time here. But in those, this acceleration, velocity, this is not v square actually, it is only v. Okay. V is equals to omega into square root of a square minus x square. So these all quantities depending on the x, which is displacement. And displacement we measure from mean position. From mean position. Okay. So for x, time equations may we have x is equals to a sine omega t plus delta, where this whole term omega t plus delta is termed as phase. And this delta itself, I will write here, delta is termed as phase constant. Phase constant. What is the function of this phase? So phase tells us about the initial status, or you can say the status of SHM. The body which is executing SHM, this phase tells us about the status of that. Like at which position it is at what time. Same for velocity. V is equals to, if you differentiate this with respect to time, so this expression you will get A omega cos omega t here, where A, in three of them, A is the amplitude. A is the amplitude, which is the maximum displacement from mean position. Okay, the maximum that a body can go in to and fro motion about mean position, that is termed as the amplitude, and omega is the angular frequency of that particular SHM. Okay, so these are relations also in terms of displacement if it is given in the question. So you will apply these formula. If time relation has been asked or something about time is given, so you will apply these formula. Now if you see the graph for fx curve, it will be a straight line with negative slope passing through origin, because f is equals to minus kx here. So it is same for y is equals to mx, where m is equals to minus k, which is the negative slope. Same is shown here in this. So this will be a straight line passing through origin with a negative slope. If you talk about Vx curve, so we know the relation is V square is equals to omega square A square minus x square. This is the relation. So if you convert it like this, V square by omega square x square by 1 square equals to A square. So this you will find out that it is the equation of ellipse. Okay. So that is why the variation of velocity with respect to displacement is elliptical in nature. Okay. Now, energy in SHM. So firstly, we will talk about the kinetic energy. Kinetic energy is given by what? 1 by 2 mv square. V we have as A omega A omega cos omega t plus delta, or phi, whatever you can choose. So if it is phi, it doesn't matter. If you take a delta here, it's also all right. Now, if you square this term, you will get this one. So this is the kinetic energy, half m omega square A square cos square omega t plus phi. Now for potential energy also, if this is a spring block system, the spring energy is given by half k x square. K you can write as m omega square. We have discussed it, how we can find out k. So if you put it here, half k means m omega square, and to x square, x we have a sine omega t plus delta. It will become a square sine square omega t plus delta, or phi. So these two relations we have as potential energy and kinetic energy. Now, if you see the variation of kinetic energy and potential energy with displacement, so this is the mean position. So at mean position, the velocity will be maximum. So that is why the kinetic energy is maximum here, but potential energy is zero, or you can say minimum. If you have taken the reference level as origin, you are measuring all the parameters from mean position, then you can say the potential energy is zero here, exactly zero, because at mean position or at the reference level, the potential energy is zero. But in general, in at mean position, at mean position, sum of E is the sum of kinetic energy plus potential energy. So kinetic energy will be maximum, potential energy will be minimum. At extreme point, at extreme points, total energy will always constant. So we can say that kinetic energy will be minimum and potential energy will be maximum. The minimum value of kinetic energy is zero, because at the extreme ends, the body will take turn, so the velocity will become zero there. That is why the kinetic energy is zero. You can see in the graph. At the extremities, the kinetic energy is 0 and it is varying as the hyperbolic curve. Okay. So this is the value. E is equals to U max at extreme points. That is the expression for total energy, half m omega square a square, which is obviously a constant quantity. So the total energy of any system in SHM, executing SHM, remain constant, and that is fulfilling the law of conservation of energy. Now, oscillation in simple pendulum. These types of oscillation you must have seen in a wall clock, okay, in clock tower. So these types of oscillation you have seen. This oscillation is termed as angular 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 oscillation or SHM. We can consider it to be SHM if the value of theta is very small. So we are going to analyze this situation. Okay, how to proceed with this? This ball here is termed as simple pendulum. Simple pendulum. So what we are going to see? We will analyze the force here. What are the forces acting on this? And based on that, we will try to relate it with angular SHM and find out the time period of this bow. Now, let's say at the extreme point, this is the angle theta at some point, and maximum it goes to theta naught, and the same way it also here goes up to theta naught. Okay, theta. Now here, let's say the weight of, let us consider mass of bob is equals to small m. So small m will act in downward direction. So force will be mg here. Now if you resolve this force, because this is executing SHM kind of to and fro kind of motion. So some of the force is unbalanced, which is causing this motion, which is causing SHM in this. So if you resolve this component, this angle would be theta. So it will become mg cos theta, and here it will come mg sin theta. Okay, got it? This is mg, the line this is making an angle theta here with the vertical. So we extend this line, this is vertical, so angle would be theta. Okay, now the tension developed in this string will be, let's say, T. So what we are going to do, we are applying the Newton's law here. Apply Newton's second law in radial direction. Radial direction. So whenever you are solving some question from circular type of motion or oscillatory type, angular oscillatory motion, always remember in your mind that you have to apply the Newton's second law in radial direction and in tangential direction. These are the two direction available for you. First is this radial tangential direction, this one, and second is this radial direction. So we are going to apply the Newton's law of motion in this direction. Got it? Now, if you apply this, it will become mg sin theta, mg cos theta, t minus mg cos theta equals to mass of bob into radial acceleration. Okay. Now, If you talk about this value, this mg sine theta and this mg cos theta, if I ask you that which one of the component in mg cos theta and in mg sine theta, which one of these component could cause the torque in this bob, or are able to, or is able to rotate this bob about this point O? Tell me. Now, the very basic definition of torque is that it is force vector cross r vector. Okay, r cross f, sorry. If you get the magnitude of it, it will become fr sine theta. Okay, now, yeah, very good. Mg sine theta we will take. The reason for that is because here the r we will always measure from the point of rotation to the point of application where we have applied the force. Okay, so the distance between them will become, let's say, L, if the length of this string is L. Got it? Now, if you talk about this expression, it is F into R perpendicular. R perpendicular means the perpendicular distance with respect to force. So this distance from the center of rotation will be perpendicular to the force. So here if we talk about, it is mg sine theta which is perpendicular to this length. Got it? Or same thing you can do with force also. You can take the perpendicular component of force with respect to the length. The same thing will be applicable. But if you talk about this mg cos theta and this L, the angle between them is 180 degree. Okay. So sine 180 will become 0. So the torque caused by this mg cos theta will be 0. So we will consider this one. Now, if we put it here, torque is equals to, we can say, is equals to I into alpha. Now, torque, we can say, it is mg sine theta force into L and negative. Why negative? If you try to find out the direction also, from F cross R, it will be negative. The thumb, if you take your right hand and apply the right hand thumb rule, so thumb will be go inside, which is negative in direction. And also one of the trick that you can take in your mind, that if the torque is trying to reduce the angular displacement, that torque would be taken as negative. And if it is trying to increase the angular displacement, that torque will be taken positive. So here the torque caused by this force will try to reduce the angular displacement. So we will take it negative. Equals to I. I is always taken about this center of rotation. So you can consider it to be a point mass from distance L. So the I will be given by ml square. Okay. Now into alpha. This you can also take it capital L. This L and this L will cancel out. M and M will also cancel out. So what do you have? You have minus g sine theta equals to L alpha, or you can say alpha is equals to minus g upon L into sine theta. Now for small displacement, for, because these displacement are very small, so for small angular displacement, Sine theta you can consider to be approximately theta. So here you will see that alpha is equals to minus g by L into theta. So from here you can say that alpha is directly proportional to, it is alpha. Okay, let me change the color for it. So alpha here is directly proportional to minus theta. So this is the condition for, this is the condition for what? This is the condition for SHM. SHM. Okay, I will tell you for linear SHM. For linear SHM, let me change the color. लीनियर एसएचएम के लिए acceleration A is directly proportional to minus of displacement, and for angular acceleration, angular SHM, alpha, which is the angular acceleration, is directly proportional to minus theta, which is angular displacement. So A will be changed by alpha, X will be changed by theta. That condition we should follow. So if you take in linear SHM further, if you take it, it will become minus omega square into X. Okay. Here also alpha will become minus omega square into theta. So the value which is written in multiplication of theta will be considered as omega. So here in this expression, if you will see, alpha is given by minus g upon L into theta. So we can compare it with alpha is equals to minus omega square theta. So omega square you will have as g upon L. Omega you will have as square root of g by L. Omega you can write as 2 pi by t. 2 pi by t, because omega equals to 2 pi into f. F is the frequency, and frequency ko you can write 1 by t. So omega will be 2 pi by t. So 2 pi by t is root of g by L. We can say that t is equals to 2 pi root L by g. So this expression you must have seen somewhere. So this is the expression for time period in simple pendulum. Okay. Now what are the special cases in that? What are the special cases? So we can say special cases, you must have noted down. So when this pendulum of mass m, and this is the acceleration, this whole setup is accelerated with angle A, alpha, and the angle between the gravity and this acceleration is alpha. So now the time period will be 2 pi root L by g effective. Now the effective acceleration you have to take, and g effective will be given by square root of g square plus a square minus 2a or 2ga cos alpha. Okay, so this formula you will use. For example, if this bob is moving in a container, and the container is moving up with acceleration a, so time period here will be 2 pi upon L upon, we know that the acceleration will be, these are in opposite direction, g in the onward direction, this acceleration is in opposite direction, so then opposite direction will add up, so it will be g plus If it is going down with acceleration a, so time period will get 2 pi L upon g minus a, or a minus g, based on whichever is greater. Okay. So these two cases you can mark important. You can take the screenshot or note it down. Once you note it down, please let me know. We will move on to the next topics. So have you noted down? Got it. Thank you. Now, why this uniform circular motion is written here? Why we need to study it? Because we can relate this simple harmonic motion with uniform circular motion. How? So firstly, we will describe what a uniform circular motion is. So uniform circular motion, when there is no angular acceleration is present. Okay. So the motion of the circle is a constant speed. This is important. Constant speed. The velocity may be variable because there always be a centripetal force. But this centripetal acceleration or this force will not change the tangential component of velocity or the tangential speed. So speed will be constant. If the speed is variable, then we will say it, this is non-uniform circular motion. Got it? This type of motion. Now, if you will observe it, this is also the uniform circular motion. You will notice down the velocity here and the force are perpendicular to each other. Okay, in this. Again, if the particle is moving on a circular path of radius a with angular velocity omega, so you will be surprised what we get. This is the setup. The radius of this circular track is a, capital A, and the velocity, angular velocity you can say, is omega. Now let's say at t is equals to 0, the particle is at point Q. The position vector will be OQ. And let's say the angle with the x-axis initial at t is equals to 0 is phi. Okay. Now what will happen at a given time t, after some time t, or after t time, how much angle it should move? The angular velocity is omega. If I talk about in terms of linear velocity, if the linear velocity is v, so in t time, how much distance it should travel? V into t, vt, if the speed is constant. So we have constant angular speed or velocity. So how much angle it should cover in time t? So it will be omega into t. Theta will be omega t. At initially it was at phi. So now it has been reached to point P, and the angle that it has been covered from OQ to OP is omega t. Total angle it has covered is omega t plus phi. Now what you can do, if you take this one OP and you resolve it into two direction, one is the x-axis, another is the y-axis. So what you will get, this total angle is omega t plus phi. This length is a. So the component that you will get on x-axis will be this, and this is nothing but a cos omega t plus phi. How we will write the component? If this is vector a, this angle is theta, the component in x direction will be a cos theta, and perpendicular direction will be a sin theta. Same thing we are doing here. The component in horizontal direction is a cos theta, theta is omega t plus phi, and component in perpendicular direction will be this one is a sine omega t plus phi. So from here you can also note that about the diameter, because this is the periodic function, okay, and you can say this is the simple harmonic function also. If you go according to the definition, we will instantly consider x is equals to a sine omega t plus phi or delta to describe the SHM. So this is the equation of SHM, which means that about the diameter of any circle, if the uniform circular motion is happening, so about the diameter, if you observe the motion about the diameter, the simple harmonic motion is executing. Similar way, mein, if you will see on this axis also, it is executing the SHM because this equation itself is the equation of SHM. Okay. So xt, this is the equation of SHM. Again, if you talk in terms of y, it will also be the equation of SHM. Okay. Now, same thing you can observe here. We have attached this blue color ball with the diameter, and this black color ball is on uniform circular motion. So if you will see, when this ball reaches the angle pi by 2 means at y-axis, so this blue color ball will be here also at the maximum from mean position. This is the maximum one. So here in this graph also, if you will see, it will lead to maximum, which is plus a. Okay. When it is reaches to pi, this much angle, this blue color dot will be at the mean position, and mean position may we have coordinate 0. So you can see here we at 0 position. Same thing for negative angle. If you will see the angle 3 pi by 2, the ball will be again blue color ball. Focus on the blue color ball. It will be in the maximum but in negative direction. So it is minus a. And again for 2 pi, it reaches to the initial position, which is at 0. This will be the. So this is how we can project the uniform circular motion with the SHM about the diameter. So we are observing the y-axis diameter, not the x-axis one. If we start observing the x-axis diameter, so here when it is at 0 angle, so the blue color wall will be here, which means the graph will start from here. Okay, graph will be like this. Okay. Now if we will plot the graphs of displacement, velocity and acceleration, so displacement is maximum at time t is equals to 0. So this will be given by x is equals to a cos omega t plus phi. Because if t is equals to 0 and phi is also 0, then cos 0 will become 1. So we can say that x has the maximum value, and simply the maximum value of this cos function will be 1. So x will be a. So cos graph will be followed here. If you differentiate this function x, then you get the velocity and get the negative value, because x is equals to a cos omega t plus phi. If you differentiate it, you will get dx by dt minus a omega cos omega t, sorry, sine omega t. Differentiation of cos will be sine omega t plus phi. So the graph will be obviously for sine, but from negative axis. Okay, so graph will be started negative position. So you can see here, if the graph of x, if the displacement is maximum, which means we are at the extreme position, the velocity will be 0. When we reach the mean position, the velocity is maximum. Although it is in negative direction, it is just the difference of direction. Okay. When we reach again the maximum amplitude, the velocity will be 0 here. Okay. Same goes for acceleration. If you again differentiate it, you will get the cos component and the negative sign will appear there. So it will become minus a omega square cos omega t plus phi. Okay, so the graph will start from negative, although this is the replica of this graph. If you will see, it is just the mirror image of this graph. Okay, now based on this discussion, we have a question here. The motion of a body is defined by the equation x is equals to tan cos 2 pi t plus pi by 3. So at t is equals to 2 seconds, calculate the displacement, speed, and acceleration of the body. So very simple, try to solve it. I am also solving it down. Now you guys firstly tell me what is the value of amplitude in this equation. Very fast, tell me. Tell me the value of amplitude and omega and phi or delta. Come on. Anyone? Any guesses? So if I write the equation here, it will be a cos omega t plus phi. Okay. So from here you can say that a is, if you just compare this equation, a is 10 meter. Okay. Although it is not mentioned here, but this distance, this is the length. So we will measure it into meter. So we have considered here that it is given in meter. Omega, which is multiply with time. So omega here is 2 pi. Okay. Now phi here is, let's say it is exactly given as pi by 3. Now we need to calculate the displacement at 2 seconds. So it is very simple. Put t is equals to 2 in this expression. So you will get x at t is equals to 2, which is 10 cos 2 pi into 2 plus pi by 3. So this will become some of the trigonometric formula you will revise. Okay, how to convert sine into cos, how to convert sine into cos and cos into sine. What is the value of cos 3 pi by 2? So these data you will just start learning or revise. So it will be 4 pi plus pi by 3. 4 pi means we have started from 0. This is 2 pi and this is 4 pi. So 4 pi plus pi by 3, which means we are in the first quadrant. And in first quadrant, all of the this trigonometrical identities or trigonometrical ratio are constant or positive. So this will be cos pi by 3 only. So 10 into cos pi by 3 will become 1 by 2. So at t is equals to 2 seconds, we have 5 meter. We are exactly at the half of the maximum amplitude. Okay. Now, if the speed is also has been asked, so again differentiate this with respect to time. So you will get v is equals to a omega cos, it is cos, so it is minus a omega sine omega t plus phi. Again, a you have 10, omega you have 20, and this is obviously minus sine omega you have 2 pi t, t will be 2 seconds, so it will become 4 pi again plus pi by 3. So 4 pi plus pi by 3, again the sign will lies in first quadrant, it will be positive, sine pi by 3 will be root 3 by 2. So it will become 20 minus 20 pi into root 3 by 2. 2 will cancel out this. So it will become 10 pi, 10 root 3, 10 root 3 into pi minus negative. Okay, meter per second. Again, for acceleration, it is your duty to find out the acceleration. You need to again differentiate this equation, put the values and get the answer. Okay. So this you will do on by your own. The same thing we have discussed here. Now, these are the two last topic that we have from this chapter is damped oscillation and forced oscillation. Okay. If you are aiming for JEE Main, this is over now. These topics are from JEE Advanced syllabus. Although some of the question has been seen in the JEE Main also from the previous years, if you will talk about. So let's study what is these topics are. Now, if you talk about the oscillation, oscillation means the to and fro kind of motion. Simply, if I take about this example, this is the spring which is attached on the ceiling, and this is the mass block M, let's say. So if you stretch this mass and release it, it will go down, it will executing SHM. Okay. But in practical life, what will happen? After some time, these oscillation will die. Okay. You are not getting these oscillation for infinite time. You have seen it. When you, let's talk about the swing. Swing you all have known about. Okay. In your childhood, you must have experienced this. So in swing also, we must apply the force. After some time, we have to apply the force to get the proper rotation, proper oscillation of it, like this. Okay. So why do we do that? Because due to the air resistance, the friction that is present or offered by the air, these oscillation will die. The energy that we get in this oscillation will expense to overcome this friction, and slowly these oscillation will die. So that type of original or practical oscillation is termed as damped oscillation. Okay, which is damped by some force. Now, so we know that ideal or free oscillation will lie forever, continues forever, because we will not consider the air friction or the actual scenario of the situation. So, but if you talk about in the real life, sometime after some time, this bow will also stop. Why? Because of the air resistance or the opposing force present into the atmosphere or the medium in which it is oscillating. Okay. So this opposing force is called the damp force, and the oscillation under this damping force is termed as damped oscillation. Mainly these damp force are air force, air drag you can say, or friction. Now, the oscillation in which damp force acts are called damped oscillation. If you consider this example, we have displaced this spring from mean position and it is continuing its motion. Okay. But slowly and slowly, what you will see, it is being stopped. Why? Because here the air resistance will also act in opposite to the velocity of it. We know that air drag is directly proportional to negative of the velocity, and this is nothing but the Stokes law. If you have remember, Stokes law is nothing but 6 pi eta r v. So it will depends on velocity and in opposite direction. Okay, and this arises due to the viscosity of the force, viscosity of the medium. Here we are in air, so the viscosity of air will also act. So due to this, we experience this system experiencing a damp force or drag force, or you can say the frictional force, due to which this oscillation dies after some time. So if you will see, this is the free oscillation. There is no air friction. There is no external effect which cause the damp in this. So you will see it is naturally, it is continuing its motion. But if you will see this, It started with very excitement, and after some time it goes down. Okay. Now, so damping force depends on the nature of surrounding medium. Whatever is in your surrounding, it will depend on that. Second thing, more the denser is the medium, more the drag force you will apply. If you will see, if you will observe that when the air blow is very fast, air is flowing very fast rate at very fast speed, that you will find difficult to walk because there is more and more drag force which is opposing your motion. Okay. Now, the damping force is generally proportional to the velocity of the bow. We have seen it in the Stokes law, and it acts in opposite direction to that. So here the damp force will be minus of BV. B is the constant. Okay. FD will be termed as damped force. Now, B is some positive constant that depends on the characteristic of medium and especially for the viscosity, size and shape of the block. Negative sign means that it is opposing the oscillation. Okay. So for a small velocity, we will use it. This is undamped, only force F is applied, which is mgl sine theta. But if you consider the damped one, it is F minus D. D is the damped force here. Now, so this will be the final equation for damped oscillation. Fr plus Fd. F realistic, that the causing the oscillation here. Fd is the damped force. So Fr is minus Kx minus Fbv. If you will take all of these calculation, you will get this second order differential equation. And if you solve it, which is not in your syllabus, then xt will be come out as a into a raised to the power minus bt by 2m cos omega dash t plus phi. So this omega dash here the angular frequency of damped oscillator, and this factor e raised to the power minus bt by 2m will cause, I will tell you, this will decrease continuously with time. So that is why this function, this entire function is not periodic. Okay? Because it will like go like this. Initially, it is at very high pace. Then as the time passes, it will decrease and decrease. And finally, it will become zero due to this damping constant. So omega you can take here. Omega dash is k minus k by m minus b square by 4m square. For small b, you can vanish this term. Again, this frequency will become the natural frequency, which is root k by m for periodic function. So if this function, because this function is decreasing constantly with time, okay. So if the decrease is very small, we can consider it to be approximately periodic, but the decrease is so high that it is not, let's say, negligible. So we can say that this function is not periodic, the general value. Now, this is the total energy. You can note it down or take the screenshot of it. This is the total energy in this expression. Okay. Now, forced oscillation and resonance. Forced oscillation means, like, what is damping? Damping is reducing the amplitude of the oscillation. To maintain the same amplitude that is decreased by damping, we must apply a force. And in SHM, the force which is acting is always periodic, because that force is also changing in direction and changing in the magnitude. A is equals to minus omega square into x, and x depends on t, which means this acceleration is caused by that force which depend on the time and which is periodic also. So by damping, if our amplitude is reduced, to get the original amplitude of the same level, what we will do, we will have to apply the same force. We will apply to have some force which vanish out the effect of this damping, and that oscillation is termed as forced oscillation, in which we put some external effort to raise this amplitude, or to get the actual value of the amplitude, which is decreased by the damping. That force, must remember, that we apply should be periodic. So in a swing, if we have observed, we have two person which is at the, let's say this is the swing that you have. Okay, here the person is sitting. So this person, and this is another person which is standing on the ground. So this person need to pull it and then push it back. Pull and push, it will do periodically. Why it is doing so? Because due to air resistance, the damping will cause the decrement in the angular displacement or the oscillation. So to get the same value or the same amount of damping, we must apply a periodic force. Okay, that is why we apply this external force to push the swing. Okay, I hope you got it with the example of swing. So the oscillating system that is driven by a periodic force external to the oscillating system, that is termed as forced oscillation. This one, look, this person, this black shirt person needs to pull this person periodically to get the same amplitude each and every time. Okay. So if a force is applied that counter the damping force, then the oscillation are called force oscillation. Simple. So in the system, we have three forces now: restoring force, which is the actual force causing the SHM. Then we have the damping force, practical force. And then we have applied the external force, which is Fe. So this will be the direction. Now, if we finally calculate this, this is something that is not in your syllabus. So finally, you will focus on this line. The energy lost due to the damping force is compensated by the work done by the applied force that we have applied. Okay. So what will happen? Initially, the body will oscillate with its natural frequency. After some times, omega dies out because of the damping, and then the body will oscillate with the frequency of external periodic force that is applied by us. Okay, and that is given by omega d. So displacement after natural oscillation die out is given by xt a cos omega dt plus phi. Omega d is the this. Now, if you get the expression of amplitude here, which is very complicated, amplitude is given by f naught over square root of m square into omega square minus omega d square ka whole square plus omega square d plus b square, and tan phi is the angle between these two, so it is given by this. You can note it all the things down. Okay, so this is the amplitude of forced oscillator, depends on the frequency of driving force. Okay, now case 1, if the driving frequency, which is omega d, is very far from natural frequency, which means the natural frequency is very greater than this driving force. So omega dB is very less than this m omega square minus omega d square. So amplitude will be given by this. Small damping will cause. Now, if second case, if driving frequency that is caused by that externally applied force is close to the natural frequency omega, so we can neglect this term. Omega should be approximately equals to omega d. So the frequency that we will get is f naught by omega dB. Now, after this situation, we got the resonance. So if the damping is small, which means B is approximately 0, the amplitude is very high. And that is the phenomena of resonance. The increase in the amplitude of oscillation of a system exposed to a periodic force whose frequency omega d is equals to or very close to the natural or undamped frequency of the system. So when the frequency of the externally applied force matches the natural frequency of that system, the amplitude will rise so high. And that phenomena is termed as resonance of the system, like this. So if the resonance is happening, you will see the amplitude is rising so high. If you take the example of Tacoma Narrow Bridge, 1914 US collapsed, it is collapsed because when the wind is blowing, it will causing the oscillation in the bridge, and that oscillation caused by that wind that is externally applied by nature will equal to the natural frequency of the bridge. So that is why there will be high amplitude of damping, and that bridge had collapsed. So it has happened because of that. Okay. So you can so why the soldier ordered to route step across a bridge. So that is because of resonance. Because if they will route their steps in order, as you have seen when they are marching, so there may be the possibility that the resonance or that the amplitude or the angular frequency by the driving force that is applied by the foot of the soldier will matches the angular frequency, natural frequency of the bridge, and the bridge may collapse. That is why they are not ordered in the route step. So this is it from my side, and this chapter is being over. Okay. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive and be regular in the classes. Okay. In the next session, we will start with wave. Okay. Hope you enjoyed this session. Thank you so much.